Hey guys, so yeah, welcome to the Apache Pinot contributor call number 4. So in today's call, we invited Aman and Xiang to kind of like introduce like what their work. So the first one is from Aman. Aman is working on a very important feature, which is called the Pauseless ingestion. This is one major kind of patch on top of the current Pinot ingestion workflow to kind of like really like eliminate uh, all the like ingestion pause during like the segment commit time, which in turn like in many scenarios, let's say if your real-time segment buffer is like quite large, and during that time you may experience like uh tens of seconds kind of ingestion pause during the segment persistent segment commit. So a mass fix is a mass like new feature is actually trying to eliminate that kind of delay, and which makes Pinot to be like continuous consuming and being serving like the all the data in the super real time kind of latency kind of scenario. Okay, I will hand off this to Aman. Aman, are you able to share? Oh, okay, you can. Okay.
You're on mute, Aman.
Oh, sorry. I hope the screen is visible to everyone.
Yes,
Looks
I
good.
can
Thanks.
see the value. Yeah.
Yeah. So the agenda for today is to discuss pauseless ingestion. The outline that I'll follow is first I'll go through how real-time ingestion looks like in Pinot and what bottlenecks did we see in this real-time ingestion, as in where did we see the pause occurring? How did we achieve pauseless? As in what tweakings were done to the current ingestion in order to get rid of those bottlenecks? And given that we did change the normal regular real-time consumption and the way it is done, we obviously introduce some scenarios where we would end up into different and new kind of failures. And how did we handle them? And lastly, I would discuss a scenario that has a lower probability of occurring, but required a lot of implementation and design from our end is the disaster recovery, where we run into a scenario where we might end up losing data in case of pauseless, which might not happen in regular real-time ingestion. So I'll get started first with the normal regular consumption. So in Pinot, most of the work is done via updates to idle state, and Helix in the background trying to sends state transitions so that the servers can continue working on a new set of ingestion for a new segment. So how it works is the controller goes and updates the idle state, stating that, hey, for this segment, these are the servers that are expected to have this segment in consuming state. Obviously, the idle state at this point, the external view at this point is offline for these or missing for this segment for these servers, and they get a state transition. When that happens, the servers go ahead and create consumers depending on what kind of upstream source we have. Let's for now take example of Kafka. So both the servers go, and when they see the segment that has newly been added, they fetch the metadata of that segment from the zookeeper, which contains which offset do they need to read from, and any other extra information that they need to create the segment. The servers start consuming, and they consume till they reach a specific threshold. In case of Pinot, we have three kinds of thresholds. One is size-based, one is time-based, and the other is row-based threshold. So depending on when they reach the threshold, uh, different replicas, they start communicating with the controller once they reach the commit threshold. Why they communicate with the controller is to tell the controller that, hey, I have hit a threshold. I want to commit this segment. And by that, it means that I want to convert this mutable segment that was in memory till now, persist it to disk, and then I too want to upload it. And I'll tell what the end criteria or the end offset for this segment is. The reason every server talks to the controller is so that the controller can be the orchestrator for this entire commit protocol. And this ensures that all the updates that are made to idle state and Zookeeper go via the controller route. So first they ask, the controller does a small leader election. For the case of row-based and size-based threshold, it is fairly straightforward. Size-based thresholds, by the way, are always converted to row-based threshold based on what has been the ratio between previous segments of size to rows. And the controller then creates the row threshold based on this previous metric and what is the expected size that we want for the next segment. So based on that, the controller, when it gets a call to commit a segment from one of the replicas, it goes and says, hey, you have reached the end offset. Maybe whosoever comes first in case of row threshold is picked as the leader. And it is asked to continue with the commit. And the other server or the other replica, if it reaches out, meanwhile, this commit is happening from the lead server, it would just go and get a keep a response from the controller. I can go into a bit detail on these two and what they mean. When a controller says commit, it expects the server to go through the entire process of building the segment, uploading the segment to deep store, and then reaching out to the controller again with the metadata that tells these are the ZK metadata basically, which says that, hey, this was the end offset. This is the number of bytes this segment contains. These are the highest and lowest values. These are the start time and end time, typical metadata that we see in Zookeeper. And uh, this is done to ensure that we don't have multiple servers going and uploading to deep store. For most of the cases, it is S3 or GCS. It ensures that there is only one server that is doing the hard work of doing the entire commit protocol, sending the metadata, and not choking the controller or unnecessarily uploading things on deep store. The server one that gets the keep basically means that, hey, you have reached the end offset, and it is in sync with what the lead replica or lead server has reached out to. You guys are on the same offset and hence have the same data. You can continue building the segment, and you do not need to move forward with the protocol. You can just keep it and stay put till I send a new state transition, which is to mark this segment as online. So the server that wins, or the one that wins the negotiation or becomes the lead for this, becomes the committing server for this segment, seals the segment locally. In Pinot, initially the consuming segment is kept in memory and some mutable indexes are built on top of it. But as and when we reach a threshold, we build all the indexes that are required for that segment and we push it to disk, that is converting the in-memory segment to something that is persisted on disk for durability reasons. Once that happens, that server now, since it was the committing server for that segment, goes and uploads that segment to deep store. Once it does that, it reaches out to the controller with all the metadata information that it needs, that it needs to populate in the Zookeeper. This is done so that in case there's a server restart or anything that happens, we can easily figure out where that segment is present on the deep store and can be easily downloaded by other lagging replicas. in case some replica, let's say, does not reach the end criteria in a given stipulated time. It can go ahead and download instead of unnecessarily building the segment again locally, that is converting the mutable to the immutable and building all the indexes. It can avoid all the hard work. Once that happens, in the end commit, in the above call that I told that the committing server does, that is the finish commit message, the controller does a bunch of stuff. The notable ones being change the ZK metadata for the committing segment by providing all the details that I mentioned before, download URL, all those other details. Additionally, it also changes the state of the segment in the idle state. So initially it was marked consuming. Now it would end up marking it as online. Once it is marked online, all the servers for that segment get the state transition from consuming to online, which expects them to load the segment. And it also adds a new consuming segment for that particular partition in the idle state. This is done to ensure that we continue consuming, in the sense that the previous one has been sealed. And now we know that we have consumed from offset T1 to offset T2. And now we can continue from offset T2 plus 1 and till we reach the next threshold. So let's briefly go through the timeline of the events that happened during the commit protocol or during the ingestion. First, as said, that the controller updates the idle state and the servers get the state transition to start the consumption from a specific offset. The consuming segment is created on the server and then it starts the ingestion. It eventually reaches the commit threshold, and the duration from starting the consumption to reaching the commit threshold depends on the rate of ingestion, the threshold that has been set. Once that is done, as we saw before, there is a leader election for not exactly a leader election, but a committing server being picked by the controller among all the replicas. After which we saw that the server that wins, or even the one that doesn't, they start building. And that is where a lot of time is spent, wherein the server or any of the replicas are not ingesting any new data. So this build time is very crucial, and we should keep this in mind when we move towards the pauseless ingestion. After this, as we saw, the segment is uploaded and there is a commit end metadata call that is made from the committing server to the controller. And the commit ends and a new consuming segment is created and the ingestion consumes. So these are the two places, these are the two points that we need to focus on. One is when the consumption stops, and second, when it resumes. So the consumption stops when we hit the threshold, and it just stays paused till we get a new helix state transition for a new consuming segment. Most of the operations that are performed between these two times are usually very fast and don't pause the ingestion for a really long time, except building a segment. For it requires creation of indexes, persistence of data on the disk, and upload, etc. But the major one that has shown to take a lot of time is the building of the segment. And that is what we try to tackle in pauseless ingestion, in the sense that building a segment has nothing to do with ingestion, and it does not in any way impact how whether or not we can ingest from our upstream. The blockade is done. So the reason for not ingesting during the building phase is because during the build phase, there is no guarantee that the segment would continue to stay on the server, as it has not been persistent on disk and it is still in memory. To avoid losing data, we do not move forward till we are 100% sure that we have the data present on disk and also have a copy of it on the deep store. So this is the sole reason why we avoided moving forward or continue ingestion before we persist something through the disk. So in pauseless consumption, what we did was we get rid of this constraint of not moving forward till we persist it on disk. When the leader election happens, instead of waiting to update the idle state and creation of a new consuming segment at the end of the process, we create the new consuming segment for when the committing server is being picked by the controller. We already have enough information to know what the end offset for this segment is going to be. And that's all we care about when we are trying to create a new consuming segment. We know that the previous segment is from offset T1 to T2, and now the new consuming segment surely has to start from T2 plus 1. So we can go ahead and start consuming from that. Meanwhile, we continue building the previous segment. So this is what we do. The current segment, and another constraint that Pinot has, or an invariant that we continue to hold, is that there can only be one consuming segment in the idle state. And for that reason, whenever, so in the current setup or in the regular ingestion, we only call a segment as online in the idle state when we know that the segment has been persisted on disk by one of the servers. We got rid of this constraint in the sense that we mark the segment online immediately as we get a commit call from one of the servers or one of the replicas, even though we know that it may or may not have been persisted on disk or present on disk. We mark that as online and we create a new consuming segment with the next offset that we need to consume. And this starts the new consumption loop wherein the Helix sends the state transition and the servers continue ingesting from the upstream. Robert, do we wait for questions or in case there are any?
Actually, that's a great moment to pause because I was just in the moment of writing a question right when you said that, because you said just a moment ago that as soon as this in under pauseless consumption, right? As soon as the segment is done consuming and it's reached its threshold, it's marked as online. And at that same time, the segment is being built. Now, what if during that time when the segment is being built, the server gets like crashes or gets restarted, right? Wouldn't that result in data loss?
So we will go to other failure scenarios. For those are the tricky ones. This will be covered in the next slides.
Okay, thank you.
Yeah.
No other questions in the chat. Please proceed.
Sure. So yeah, this is the basic change that we did. And obviously it came with a bunch of challenges, like one pointed out by Robert, wherein you can have a server crash, you can have a controller crash in the middle of the commit protocol. Anything and everything can go wrong in between. The segment build can fail. The upload to deep store can fail. So there are a bunch of challenges that we faced while we were trying to design it and come up with a solution as we are moving forward even before we seal the segment or persist it on disk. So these are the bunch of challenges that we saw. What if the segment build fails? What if the commit server gets restarted? And what if the current consuming segment is marked online but is without a copy in deep store? How do any other server that's coming online, any coming or restarting, download it? Where should it download it from? So let's segregate these challenges into two. One are those in which at least one of the replicas has the segment, and those that in which we run into a situation where none of the replicas have the segment, in the sense that all of them restarted uh, after the segment was marked online and none of them have it on the disk. So to handle the first case of failures where at least one of the replica has the segment, what we do is at the server level, when a server gets a state transition, let's say the committing server failed and the replica 1 had the segment sealed locally or is in the process of sealing locally, the committing segment that restarted would on the time of restart would check the ZK metadata and see if there is a download URL present or not. If there is no download URL present, what it would do is it start doing peer download, in the sense that it would figure out whether any other server hosting this segment is marked online in its external view. So if the server is marked online in its external view, it surely has the segment on disk, and hence we can go and request for a download of the segment. So this solves the restart problem. And to ensure that the server that is restarting or that has lost the segment in memory segment doesn't fail, we do this periodically for a default of 10 minutes. This is configurable. We do this because we do not know at what time would a segment be sealed on another replica. The only time we try to uh, download or load this segment is when the segment has been marked online, and the segment is marked online only when the initial leading or committing server has been selected. So we gave 10 minutes from the time the segment has been marked online in the idle state by the controller till for 10 minutes, so that one of the servers, at least if in case it is able to build and uh, host the segment on the server on disk, we can just go ahead and download it. This solves two problems. One is obviously restart. Second is upload failures. Since Uber initially came up with this approach, as they had a lower availability of their deep store than Pinot, they came up with this workaround where they go and download it from one of the servers that is hosting the segment. We just piggybacked on that and tried to solve the first set of failure scenarios that we came across. Now, the second type of failure scenario is that of no servers hosting the segment, or there is no local copy that is present anywhere on any of the replicas. In that case, what we do is there is a periodic job that so obviously the answer to this is going to be you have to go and re-ingest the segment. You have to go back in an offset. Meanwhile, you continue with your normal ingestion. You have to go and since you have the ZK metadata of the start and end offset, you know from where to where you have to ingest and how many rows are there in that segment. We have all the metadata necessary to know, to avoid duplication, to avoid data loss. Now the tricky part is, how do you know none of the servers have the segment? How frequently do you check this? And how are you sure that you upload eventually? And how do you send a transition to each of the servers and ask them to load the segment again? So these are the bunch of challenges that we came across while we were trying to solve this problem of disaster, in the sense that no server has the segment anymore. So what the controller does is that there is a periodic job, real-time segment validation manager, that runs periodically on the controller. It checks the external view and idle state and sees what segments are in error state on all the servers. The reason for checking all the servers is to ensure that there should not be a scenario where a server might be building a segment and we start re-ingesting it unnecessarily. So to avoid that, we ensure that the segment is in error state on all the servers. And once the controller ensures that, it picks one of the servers and sends a reingest call. The server then just follows the normal reingestion and sends back the metadata that it would have had it done a commit end call that it was doing after the building and upload phase. It does exactly that and then calls the controller. The controller goes and updates the metadata in the ZK and sends a reset message to all the servers, resets the segment. This ensures that all the servers get the state transition to load the segment. And here, since they don't have the segment locally, they go and check the segment ZK metadata and find the download URL and easily download and load it on the disk. This is how we were able to ensure that we do not have any missing data. Obviously, it comes with the challenges in the sense that the periodicity of the validation manager would determine how long we have the missing data. Does that answer the question, Robert?
Yes. So you're saying that the controller is basically checking for this disaster scenario. I forget which class or specific implementation you mentioned, but essentially is doing like a backfill of that segment and issuing a command to one of the segments to re-ingest that missing segment. Or
Correct.
yeah.
So yeah, these
And so
are
when
few.
it's doing that backfill, it's kind of doing it in parallel with the consuming segment, right? Like that
Yes,
backfill doesn't cause any delays.
yes, that runs in the background and has nothing to do with the normal ingestion that goes through the Helix path. This is more like an API call that is made by the controller to one of the servers. And it's just a normal message exchange between server and controller, wherein once the server is done, it just reaches out to the controller stating that, hey, I have been able to ingest this uh, previous and old segment that you thought had failed. And here is the metadata for that segment, and then the controller just goes and updates that metadata. Obviously, the idle state is already online, so it does not need to do anything on that part. It just resets the segment, which then follows the Helix state transitions of offline to online. Is there any other question?
No other questions, please proceed.
Sure. So yeah, we saw huge improvements in trying to remove this bottleneck of segment build that we saw was introducing 3 to 5 minutes, and in worst case scenario 10 minutes of delay. It also something that we did not anticipate would become a problem, but we have seen customer face issues, is that of segment build wait times. That also got resolved because of this. So segment build times are those is the time that the server spends in building the segment. But given that the segment build is a very expensive process, there is a restriction on the number of parallel segment builds a server can have. And this leads to the issue that if there are multiple partitions being hosted by the server, or multiple tables or segments being built by the server, they are queued and they wait for them to attain the semaphore or start building. And this leads to a lot of wait time. And by going through the pauseless ingestion, we were able to eliminate both the wait time and the build time as we start the ingestion at the commit start itself. So when we enabled pauseless for one of our customers, what we saw was that at peak 40 million events that were being ingested per second, the delay that initially was well over 10 minutes in worst case scenarios, or 15 minutes in worst case scenarios, dropped suddenly to below 5 seconds, and in worst case went at max to 7 to 8 seconds. Yeah, I think that's probably it when it comes to pauseless ingestion. I'm happy to take any more questions or go into any more details if anyone feels so.
If anyone has any more further
Yeah, I think this feature is very critical for what we've added like for the past years, and we have also been in active discussion of like making this mode to be the default mode for Pinot ingestion. So yeah, I think this is like very important, making the Pinot to be the super fast and super low latency kind of ingestion, both like a query and ingestion. Yeah. Okay.
We had one question in the chat come up from Uday.
Okay.
He asked, since segment re-ingestion can take some time, would queries return stale wrong data?
Yes, the queries will get impacted, and that is one concern, in the sense that we have to figure out a way to balance how fast we want to go and how much is the importance of recent data versus how much do we want to focus on durability. If durability is a really big concern and we can't have missing data at any cost, then normal ingestion could be the way to go. But if we are okay in having partial results, that too in very rare scenarios, like I pointed out, this would be a disaster scenario where none of your replicas have the data. In those cases, there can be periods where you have partial results come up.
Yeah, so in general, I think this disaster recovery or whatever things is being so how to say, like in that scenario, it means you're already having the outage, which means because they are like more than, let's say if all your replications are gone, right? So it means you're already having the outage. And in terms of that, how to quickly get back the system and making all the data ingestion happen, that is more important. So whatever the disaster recovery here is try to ensure there's no data loss from the whole system perspective, and there's always a way to bring back the data, even if the previous online segments, all the local and remote data copy are lost, there's still a way to get back the data. All right, so let's get to the next one. So for the next topic, we'll invite Xiang to talk about how to ingest the semi-structured JSON data into Apache Pinot. Yeah, we'll hand off the stage to Xiang.
Yeah, thanks, Xiang. So we'll start. Yeah, can you see screen in the slideshow mode?
Yeah, looks good.
Okay, nice. So yeah, hi everyone, this is Xin. So I will talk about how to ingest semi-structured JSON data into Apache Pinot. So first of all, the semi-structured data has become more and more popular, especially in the observability use cases. So they don't have static data mapping. And the top concern or top question to ingest them into Pinot is like how we map this semi-structured thing into Pinot's fully structured schema. So yeah, let's get started. And this is the agenda. So first I will talk about some background about Pinot real-time ingestion. Then talk about something about semi-structured data, semi-structured JSON data. Next, we will talk about the data modeling, how to deal with this data ingestion. And then we will introduce our core component called schema conforming transformer, which is to ingest this semi-structured data. And we will briefly talk about what's next. So first, this is a kind of like high level how Pinot real-time ingestion works. So at the beginning, there will be a stream client, for example, Kafka client, to pull data from the Kafka broker. And then after pulling, this is usually a batch of messages. They will be in the bytes format. With this bytes, then Pinot will use the stream decoder. This is usually specified by the user in the Pinot table config. The decoder will decode this bytes data into Java objects. So in Pinot, it's called generic row. This will represent the data in a Java format to be used. And then we will go through a series of transformers. So in Pinot, I think there are like you can specify like a lot of transformers to convert data. They are both in generic row format, but the input generic row is more close to the stream data format. The output generic row is more close to the Pinot schema format. And at last, the generic row will be fed into the mutable segment. The mutable segment will do the indexing or Pinot's encoding for the data. So this will have a deeper look on how this works. So for example, on the decoder side, the decoder will based on the encoding format of the stream data. So some very popular formats are, for example, Arrow, JSON, protobuf. specified by users because they need to know in advance that what the data format looks like. Then this generic role in Java is usually like a map of string objects. So it could be very flexible to represent the input data, and this has to and usually matches the input format, which means like the schema of this map of string object is kind of very close to the streaming data, but may not be close to or same as the Pinot schema. So how to mapping them is like these transformers. So Pinot has a lot of different types of transformers. I just list a few examples that is very popular. For example, expression transformer, we can use this transformer to generate some new data, new column data based on the existing column data, even with some, like, for example, if-else logic to embed it. Filter transformers, for example, with this, we can leave some rows and filter out some rows. To get less rows, that's what we only need. Then schema confirm transformer that we will talk about is can also be part of this. Data type transformer is kind of mapping the input data format into Pinot's data format. For example, some like time or JSON data format. It do some sanitization on, for example, multi-segment, multi-value or single value. Those kind of sanity check are also in this data type transformer. Then it goes to another generic role. This role is same thing with Java object map of string object, but the key value pairs will be same as the Pinot format, Pinot schema. So we will have some example in the next session to talk about how different those two things can look like. So yeah, this is a general how Pinot ingestion works. And we will then talk about how to ingest JSON data. So first of all, JSON data, it may not be like a JSON from input. For example, if the input is Avro, it could also be in general meaning like the JSON in this talk. So for example, in Avro, there could be like a map format. This map format can be nested data. So JSON data is usually nested, and there's no strict constraints on their key value schemas. So for example, they can have some keys that always present. They can have some keys that's only this row of JSON has. So this makes JSON could be like very dynamic and also is highly nested. So first of all, how to store them. So in Pinot, there's already a data format called JSON in Pinot schema. And we have JSON index to index JSON data. So they are able to be used to ingest, like, for example, if you have a big row of data and only small portion of them JSON, then it's totally fine to use that JSON indexing or JSON data format to store it. But it's usually inefficient to store everything, the raw data, in the JSON format. So first of all, the compression ratio is very, very low. So Pinot is a columnar database, and like dictionary encoding is very important to reach the high compression ratio. So for example, if you store everything here as JSON data, raw data in Pinot, then for every single message, you need to store every keys. For example, this trace ID key. So for every single message, you have to have the trace ID written there. But if you extract it, then you only need to have one key stored, and for each rows, you only store their value. So that's one thing. The other thing is like encoding wise, there could be duplicated data inside your input. But if you store everything in JSON format, then they cannot be compressed efficiently. Second thing is like indexing support. So with JSON index, we have some support on JSON, but it's a bit memory heavy, and the performance is not as good as, for example, inverted index. And also, if you want to do something like text search or range search, then JSON index may not be that powerful. So that's a limitation of the JSON index, and why we need some special treatment to store the JSON data. Then to store it, like we need to analyze the type of JSON data. So we can start with a simple version, which I call it structured JSON data, which means like the fully structured JSON data. So taking this example, let's assume like the JSON is very static. So for every single row of this JSON data, you have same keys. So even though they are nested, they are same keys. Then for this case, like the problem we are solving is just like unnest the JSON data and extract them out. So to do this, like Pinot has some support called the complex type transformer. We have it for many years. So we can use this complex type transformer to unnest all the keys, kind of flatten all the keys from the input JSON. And then we just do the static mapping one-to-one to store them inside the Pinot schema. So it's still a static to static mapping, and the problem is not that hard to solve. And it can also have very good performance because we can still utilize all the benefits that Pinot provide. And the next thing is like what we are talking about today is semi-structured JSON data. So semi-structured means it's not fully structured. Some keys, they always present. Some keys, they may be like a dynamic and only present in some rows of the data. So in this way, like we can now really do some static mapping by unnesting keys, because there will be some keys that you will never know. For example, till today, there's no such keys, but tomorrow user might provide these keys into data. So this is very common in, for example, observability use cases, like in logging data. People may create some new logs in any days, and you can never predict it, and this may cause some issue with the static mapping. So that we need some like intelligent data modeling to treat this scenario. Okay, then we goes to this data modeling phase. So samely, we taking this, for example, this is like trace data, which is kind of observability data as an example. So there are some keys always present. There will be some keys present frequently. There will be some keys present very rarely. So we need to analyze them and categorize those keys into different categories. So first, we pick some keys that always present in every single row of the message. So for example, in this tracing use cases scenario, so we can see like trace ID, spy ID, those keys are like always there. Then of course, we need to make them as dedicated column to use the benefits we can have. The second phase, we analyze the keys by the frequency. So for example, there will be some keys that's frequent enough. Let's say we have threshold like 10%. Then if the frequency of this case cross that threshold, then we promote them as the dedicated columns. For example, here in the attributes, this nested structure with the attribute component, or like a resource attributes host name. So this could be the very nested structure. We also make them as the dedicated columns. So this nested structure with these dots padding is kind of aligned with how Pinot JSON index define the data nesting. So here we can also make them as a dedicated column. And then for the less frequent columns, for example, they appear very rarely, and we cannot predict their appearance. Then we will put them as something called JSON data. Leave them in the JSON data because they are very sparse. It's not a big deal. We don't have high conflict ratio on them. We leave them in JSON data and put them in the same hierarchy. So for example, if they are nested in like 3 layers, 2 layers, we keep them same in this JSON data. And here is optional, like if you want to do the text index, we can have some meta index to do the text indexing for them. So this part I will talk later. So this is the overall like data modeling of the semi-structured data JSON ingestion. So the high-level idea is like we want to utilize Pinot's column data storage, and so that we want to extract the data into dedicated columns as many as we want. But meanwhile, we don't want the column to be too sparse, which means like we have this column, but most of them, or close 100% of them, are non-value. Then it's kind of meaningless to extract them as dedicated column. So to reach this kind of balance, we make trade-off so that we analyze the frequency of keys and put them into 3 categories. And to the end, they will be lie into 2 Pinot type of columns. One is static column, the other is like a JSON data, which has to store those long tail data. Okay, next is the schema conforming transformer. So here we can go back to achieve this kind of data type extraction. So we need to find a place to achieve this inside Pinot ingestion pipeline. So theoretically, we can also do this in the decoder, but usually it's not recommended to do that because decoder is usually to do like a one-to-one mapping to keep the data in the original format, but just make byte data into a Java object. So that transformers is usually like best place to do this mapping from one type of Java object to the other type of Java object that is easily fitted into Pinot's schema. So that we introduce this schema conforming transformer as one of the transformer in the Pinot transformer pipelines. So here, yeah, we go back to the schema conforming transformer. We have this feature fully ready in the open source, and we have documents in the doc page. So taking the left side, Kafka message as example. So here I have different formats of data. For example, you have string, array, different nested map, and some nested map. So here we can first put out the schema. So let's say we have those 4 type of schema: array field, map field, nested field, and nested field dot string field. So and then we have 3 like reserved column with JSON data, JSON data no index, and merge index. So previously we talked about dedicated columns and JSON data. So those are usually like indexable columns. But there's cases that user store some data, but they never search on those keys. Then for those things, like we expose a config in the schema conforming transformer so that we can store those data, but without indexing them. So that the long tail of that part will be called JSON data no index. And multi-index is optional for the text search that we will cover in later sections. So this will be the transformation like outcome. So with left side is input generic row, right side is the output generic row, which is after the transformation. So the black part is what we put in the schemas, those 7 keys. So here we can see like for the array field, we can put it here, we can extract them. For the nested field or string field, although it's nested, we can also extract them out from this nested field and dot string field. We extract them out. But for the map field and nested field, we will leave them as none. The reason of doing this is like the extraction of the schema conforming transformer is through what we call leaf node. So which means like if we analyze the input data and find that the key after we analyzing and find the key, for example, map field, we go to the input data and find this map field key. But we found that the value of this map field is another map, which means like it's not a leaf node. Then we usually need to go into this map field and extract again. So this is to kind of solve the conflicts between, for example, we can define map field and map field.string field. We can define the schema with both keys present. And we usually want to go into the leaf node to make sure we can store the data that can be best dictionary encoded, best representative for that dedicated column. So in this case, the map field and nested field, they are not leaf node. So we will leave them as none. And instead, they will keep in the JSON data. For the JSON data no index, this is an extreme case that we have so many keys that does not need to be indexed. But in most of cases, we don't have much there. So we can focus on the left side, the middle column first. So you can see that for this example, it's not very efficient for the extracting because the schema we defined cannot really represent the data format. There are still many keys in the JSON data that are not extracted. So instead, to improve this, we need a better schema design for this. So here is another example. So instead of 7 columns, here we have 10 columns with some different columns based on our learnings from the data, raw data itself. So that with this case, we can see that we can extract data more efficiently. So here, most of the data can be extracted. Either they are already flattened data, or they are nested data, and we flattened back in the transformer. And we leave some more dynamic field, which is less frequent field in the JSON data itself. So most of common fields, we extract them out, but the less common field, we put them into the JSON into the JSON data. That's kind of how schema conforming transformer work. But here the limitation is user always needs to define the schema of it. So we don't have this kind of intelligence in Pinot yet. So there needs to be some ecosystem build around Pinot. For example, you kind of sampling your input Kafka message and come up with your schema. Or you have the insights of data already, and then you use that insight to form your data schema. Okay, so so here we already extracted everything out, and then we can go to one optional feature of schema configuring transformer, which is to do the text search. So when we design this schema configuring transformer, it's mainly used for the observability case. So for example, logging. So to help build this logging system, so we usually need a text search for it. So we have this multi-index field, which is a list of values. So this value is kind of begin anchor, value, separator, key, and end anchor. So taking an example from the previous slides. So for example, this string field, then the key is string field, this word. The value is this A. And we put them in this format so that it can be easily to be searched in a kind of Lucene searching pattern. And we have a configurable indexing scope. For example, user can choose to have some keys to be text searchable and some keys not to be text searchable. So if your keys is text indexed here, which means you put as part of this list of keys in the multi-index, then there's possibility that you can do the text search with this syntax, text match, multi-index, and then, for example, you want to do exact match on the key value, then you can do value key with this separators and delimiters you choose in this list. So I will give more example. So for example, if you want to do the exact key value match, then the syntax is text match, multi-index, value, and key. And if you want to do the wildcard search, it's also possible. You can do the text match, multi-index with some begin and wildcard around this value. So same for the keys. You can check if the key exists by do the text match that you search for a key and value you leave a wildcard. Or you can do a global match. For example, you don't know the key of this of the value you want to search, but you can also search this value around all the keys you have in this merge index. That's the reason we merge everything into this merge index, because you can do the global value match like this. Similarly, you can also do the wildcard global match with similar format. with the value you want to search and some value cards around it. So yeah, that's basically the text search of it. And I also list off some next. So first, right now the schema generation recommendation is kind of based on user input, or you need to build an ecosystem around Pinot to generate the table schema. So one potential next investment is like we can put this inside Pinot so that people can use this out of box. The second part is like intelligent query generation. So here with schema conforming transformer, like based on schema, the data could be ingested in like different way. And usually the schema is evolvable, which means like the user will always generate new keys into the data. They will remove old keys from data, so that the schema, the best schema of your table needs to evolve time to time. So with that, if users want to have like a very stable query experience, they usually need to like fetch the Pinot schema first, and then generate some query language or query they want to send by using the Pinot schema. So that part needs some actual work that we may be able to invest more and make it more intelligent. So yeah, last some acknowledgement. So this feature has been contributed by like both Uber team, like Team Chris, as well as some folks from Abesco, like Jack and Kirk. Yeah, last, any questions?
That was awesome, Xiang. Thank you so much for providing all that detail. My question is for a couple of questions. The schema conforming transformer, is it purely based off of the table's schema and the way it does the transformations, or is there some like additional configuration that it uses?
Yeah, there's a configuration. So we have so first, yeah, thanks for the question. So first we have this page for the schema conforming transformer in the Pinot doc, and here list of a lot of configs that you can choose to use for this transformer. So can refer to this doc on how to use it. So for example, if you want to keep the JSON data, or if you do not want to keep the JSON data, or for example, if you want to skip some storage, drop some messages, or for the text search, you want to have some limitation on each key values. So yeah, something like that. This is fully configurable here.
Then my second question was in comparison to the previous complex type transformer.
Mhm.
Are there any cases where you would still want to use that instead of the schema conforming transformer?
I would say like if the data in the input data is fully structured, then usually you can use complex type transformer. But you can also choose the schema conforming transformer. Schema conforming transformer is like more flexible. They can cover the use cases that complex type transformer use, but not the other way. But if you want to do like fully structured data, then complex could be like a very good choice on it.
Would it be a better choice? Because it seems like the schema conforming transformer provides like a superset of the features that complex type transformer provides.
Yeah, you can understand like that. So if you do not need to use the other feature that the schema conforming transformer provides, then you can use complex. But for example, even for the fully structured data, if you want to build a text index, then schema conforming transformer could still be a better choice. But if you do not that, and everything provided by complex transformer already meets your requirement, then yeah, you don't need to invest the other solution.
Yeah, so you're saying use the schema conforming transformer in those cases where you have, really semi-structured, and just continue using complex transformer if your JSON is static.
Yes. And also like a schema conforming transformer has the text search. So if you want to use text search, then you can choose the schema conforming transformer.
That's because it
It's built the
it adds the index to the
to the input.
Nice.
Any other questions?
To do the same thing with you would have to like manually add the index when using complex type.
Yes. Then in that way, then it's better to use the schema converter transformer because everything is already provided there. Oh, if no other questions, I can stop. Yeah, thanks.
Yeah, I think it's good. So yeah, thanks, Xing, for giving the presentation to introduce this feature. And we'll also close this this core and looking forward to the next one. Yeah, thanks, Xing. Thanks, Robert.
Thank you.